Okay, guys, I'm sorry. There were a few slides missing from the part 3 PowerPoint for the blood vessels. So I'm just going to go over those slides that were missing with you real quick. This slide right here is just talking about the way that the blood vessels or the capillaries shift from filtration out of the blood to reabsorption back into the blood, right? So if we look at, like, say this was our capillary, right? The blood comes into the capillary over here. So like this would be the arterial. It flows through the capillary and then it leaves the capillary via the venule. In the beginning of the capillary, net filtration pressure is positive, right? It's really high. That's because hydrostatic pressure pushing out is greater than orthostatic pressure pulling back in. So overall, we're filtering, right, or we're pushing out of the capillary bed. Then as we get to the venous end of the capillary bed, or like the end of the capillary bed, overall, we see that the net filtration pressure is negative. That means that there's more force pulling back in than there is pushing out. That means we end up reabsorbing at the end. So when we first flow into the capillary bed, we tend to push fluid out. That's filtration. At the end of the capillary bed, we reabsorb back in. Now, this transition point between filtration and reabsorption is not directly in the middle of the capillary. So the amount that we filter out and reabsorb back in, they're not equal, they're not the same. The spot where we go from, where we switch from filtering out to reabsorbing back into the blood is closer to the venous end of the capillary. That means that the capillaries filter out more fluid than they reabsorb back into the blood. Okay, so we filter, 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 and then just reabsorb. Okay, so more fluid gets pushed out of the blood than gets pulled back in. On average, about 24 liters a day is pushed out of the bloodstream. 20.4 is pulled back in. That means that there's an extra 3.6 liters of fluid every day that gets pushed out of our blood into the interstitial fluid out here and does not get reabsorbed. That fluid has to go somewhere, right? Otherwise, I mean, if it didn't make its way back to the blood, we would literally have no blood volume at the end of like 2 days. So this is like total all over the body, right? There's a little bit more fluid everywhere in all areas of your body that gets pushed out of the blood but does not get reabsorbed back in. What happens is that fluid ends up entering our lymphatic system. Okay, so here you can see that happening. This is showing you kind of a simplified capillary. Normally they exist as capillary beds with a bunch of different vessels, but this is just showing you a simplified version. So keep in mind this side over here, right on the left, is the artery side where the blood is coming in. Then the blood flows through the capillary bed and eventually it leaves via the venule side. So as the blood comes into the capillary bed, there's a lot of pressure pushing out, so we filter a lot of fluid. Then we get to the point towards the end of the capillary bed where there's not as much pressure pushing out, but we still have this hydrostatic pressure. I mean, we still have this osmotic pressure because of all of the plasma proteins that are here in the blood. So that pulls fluid back in, and that's reabsorption. Again, this point where we change from filtration to reabsorption is not exactly in the middle. We filter more fluid out, then we reabsorb back in. So that means that we end up with an extra 3.6 liters per day of fluid that gets pushed out into the interstitial fluid and does not get reabsorbed. So what happens to that fluid? It does not just stay in our interstitial fluid. Again, it enters lymphatic circulation. So when you look in the body, we have blood vessels running all throughout our body. We also have lymphatic vessels. This is another set of vessels. They don't have blood running through them, they have lymph running through them. So there are little lymphatic capillaries, right, that start out here in the body, and all of this extra interstitial fluid, that's pushed out of the blood and then it's just accumulated around our cells, that extra fluid enters into the lymphatic capillary and it flows through the lymphatic capillary. As the lymphatic vessels carry the lymph through our body, every once in a while they'll go through what's called a lymph node. So that fluid, that lymph, gets pushed through the lymph node where it is cleaned and filtered. It comes in contact with a bunch of different lymphocytes. If there's an infection present, we alert the immune system. And then that lymph carries on the lymphatic vessels, right? And this happens until the lymph makes it right up here to where the subclavian vein is, and then the fluid gets dumped into the subclavian vein. So that liquid started out in the bloodstream, right? It got pushed out of the blood in the interstitial fluid. Then that fluid went from the interstitial fluid into the lymphatic vessel as lymph. Flows through the lymphatic system, it gets cleaned and filtered, and then it gets dumped right back into the subclavian vein, into the bloodstream. So this is kind of a way to just circulate fluid through the body and make sure that this fluid is being exposed to the immune system to check for infection. Now, as always, there are situations where things don't happen correctly and we have disease states that can occur. Edema is something that can occur if this balance between filtration and reabsorption is off in some way. So edema is swelling, literally just like when a body part swells. This happens because of an accumulation of interstitial fluid. So when there's too much fluid surrounding our cells and that fluid starts to build up, that area of the body will start to swell. Edema or swelling occurs when there's a disruption between hydrostatic pressure, which pushes out of the capillary, and osmotic pressure, which pulls back into the capillary. When we have a disruption between that balance, we end up pushing extra fluid out of the blood, more so than we normally would. There is already an imbalance between filtration and reabsorption, right? Remember, we already have 3.6 liters a day that gets pushed out of the blood and goes into the lymphatic system. Edema occurs when there's even more fluid than that gets pushed out of the blood, or when we can't drain that excess fluid through the lymphatic system. Right? If any of this that system is messed up, then fluid will start to accumulate in our interstitial fluid, and that's swelling or edema. So there are all different types of things that can cause edema. One, and this is probably the most common thing that all of us have experienced, one is tissue damage. So think about it, right? Remember, this is our artery side, the blood comes into the capillary, and then over here is the venous side. If there is tissue damage, right, say this blood vessel is broken right here, then we're going to have extra fluid leaking out of the vessel into the interstitial fluid. Also, if you damage the capillary wall, right, if you break the capillary wall, then the plasma proteins can leak out of the blood and into the interstitial fluid. Plasma proteins are the things that give the blood osmotic pull down here in the venule side, right? Because those big plasma proteins are stuck in the bloodstream, it pulls fluid back into the capillary. If those if those plasma proteins are not in the blood any longer, then the blood does not have that osmotic pull. And the plasma proteins are actually out here in the interstitial fluid. So relatively speaking, the interstitial fluid actually has more osmotic pressure. So that would prevent reabsorption from occurring. So we push water out, we don't pull it back in, so water accumulates outside of our cell, outside of the blood in our tissues. Starvation can also cause edema to occur. The reason for this is you need nutrients in order to produce plasma proteins. your liver produces your plasma proteins. And again, it's these plasma proteins that give the blood the osmotic pull to reabsorb fluid. If you don't have amino acids available, you cannot produce plasma proteins. So you don't have that osmotic pull. Frequently, when a patient's suffering from starvation, the accumulation of fluid or the edema occurs in the belly. This is called ascites. Okay. Ascites is edema in the stomach or in the abdomen. So the abdomen starts to grow and protrude because of that edema that's occurring. This is why, like sometimes if you've ever watched articles or news stories on children, this happens frequently on the continent of Africa, of children who are suffering from starvation and their belly is sticking way out. And it seems weird because you're saying, okay, this person's starving, why is their stomach so big? The stomach is not fat. It's not big because it's fatty. It's big because it's full of fluid. There's a lot of fluid accumulating there. Ascites can also occur in patients who have liver failure. If you have liver failure, you cannot produce plasma proteins, right? That's another reason why fluid would accumulate. You can't produce the plasma proteins because the liver itself is failing. Those patients frequently have ascites as well. Anything that increases circulatory pressure, or blood pressure, would cause edema. Remember, we have a balance between filtration out of the blood and reabsorption back into the blood. Well, filtration is driven by hydrostatic pressure, right? That blood pressure. So if you increase blood pressure, you're going to increase filtration, so you can have fluid accumulate. Increased blood pressure, for example. Also, heart failure. Heart failure is a big one for causing edema in the lower limbs, like in the legs. We call that pedal edema when it's the feet. Or blood clots. Blood clots can also associate or cause edema. Okay, so tissue perfusion refers to the blood flowing through our tissues. So all of our active tissues have to have adequate perfusion. They have to have enough blood flowing through them. The reason for this is that the blood carries oxygen and nutrients to our tissues, and it carries carbon dioxide and other wastes like uric acid and lactic acid away from our tissues. So you have to have enough blood to deliver the good stuff and take away the bad stuff. Tissue perfusion, right, or how much blood is flowing through the tissues, is affected by cardiac output. So how much blood does your heart pump? Peripheral resistance, right, so how hard is it for the blood to flow through the vessels, and blood pressure. When tissue perfusion is inadequate, so when we have a tissue or organ that's not getting enough blood flow, there are numerous different regulatory mechanisms that adjust cardiac output, peripheral resistance, and blood pressure in order to adjust blood flow to make sure that our tissues are getting enough. There are 3 levels of control when we look at things like, cardiac output and blood pressure. We have auto-regulation, neural mechanisms of control, and then endocrine mechanisms of control. So we'll start with auto-regulation. Auto means self. So auto-regulation is like self-regulation of blood flow. This is when there are some little local factors, right, like little local chemical messengers that cause an immediate localized adjustment in blood flow. So there's a cell, that cell's not getting enough blood, so it releases chemicals that go right in that area and increase blood flow. Right? It didn't need the brain to fix it. It didn't need some hormones or neurotransmitters to fix the problem. That cell or that tissue fixed the problem with blood flow by itself. It auto-regulated or fixed its own issue. So the way that autoregulation works is the chemical messengers either dilate or constrict the precapillary sphincters. Okay, so this is why it's just adjusts blood flow in that one little local area. We have local vasodilators and local vasoconstrictors. Local vasodilators are things that increase blood flow at the tissue level. Right? These are compounds, or these are things that would cause the precapillary sphincters to dilate. Right? So they cause dilation or opening up of the precapillary sphincter. If the precapillary sphincter relaxes or dilates, more blood flows to that part of the capillary bed, which fixes whatever the problem was. So things that act as local vasodilators include low oxygen concentrations or high CO2 levels. So low oxygen means hypoxia. If part of the tissue is hypoxic, that would cause the precapillary sphincter in that area to dilate so that more blood could come to bring more oxygen. Or if the area has high levels of CO2, right, hypercapnia, that would also cause more blood flow in that area. A low pH, if the pH becomes too acidic, for example, because of lactic acid buildup, which occurs like when your muscles are really active and they have to start producing ATP anaerobically. Remember, lactic acid can build up. That's another thing that would increase blood flow to that area. And then also nitric oxide. Nitric oxide is a local vasodilator. Local vasodilators are much more common. We very frequently will tell the sphincters to dilate, to open up for a little while so that we can get more blood flow to an area. Local vasoconstrictors are more rare. It's less common for us to tell for us to have part of a tissue that doesn't want blood flow. Thromboxanes are examples of chemicals that can act as local vasoconstrictors that can decrease blood flow in one little area of a capillary bed. Thromboxanes are compounds or chemical messengers that are released by activated platelets. You know that platelets get activated when we are bleeding, right? When there's some sort of a bleed in an area. Well, this makes sense. If you have a vessel that breaks and you're bleeding, you don't want more blood to come to that area. So it would make sense to have thromboxanes cause precapillary sphincters to constrict so that you don't bring blood to that area where you have blood being lost through a bleed. So thromboxanes are local vasoconstrictors. They constrict they cause precapillary sphincters to constrict in order to decrease blood flow in that little area of the tissue, so at the tissue level. Again, these are all mechanisms of autoregulation, right? So when we say constriction and dilation, in this situation, we're not talking about big vessels, right? We're just talking about precapillary sphincters, so we're altering blood flow in one tiny little area of tissue.